Have you ever actually stopped to think about how incredible it is that you can just toss your phone onto a pad and it instantly starts charging? No plugs, no tangled cables, just power seemingly leaping right through thin air. It feels like this invisible magic trick that we completely take for granted every single day. But what is actually happening in that tiny little gap between your phone and the charger?
Welcome to The Explainer. Today, we're unpacking the fascinating science and history behind wireless power transfer. Based on some incredible research and industry data, we're going to break down the invisible energy field sitting right on your nightstand and see exactly how this technology is scaling up to change the world.
Okay, let's dive into this. Here's our roadmap for today. 1. The magic of invisible power. 2. Electromagnetic induction and resonance. 3. The secret digital handshake. 4. The Q2 charging revolution. And finally, 5. Wireless charging the future.
Section 1. The magic of invisible power. A century in the making.
To truly understand where we're going, we kind of have to look at where we started. And the whole idea of cutting the cord is actually way older than the modern smartphone. Our timeline begins over a century ago, back in 1901, when the brilliant Nikola Tesla built the Wardenclyffe Tower in New York. He backed it with a massive $150,000 investment, and his ultimate goal? To wirelessly transmit electricity across the entire globe. Now, while financial issues stalled his dream around 1905, he absolutely laid the groundwork. Fast forward through a century of stagnation to 2007, and researchers at MIT made a massive breakthrough. They successfully lit a 60-watt light bulb from 2 meters away using magnetic field resonance. Just a year later, in 2008, the original key wireless charging standard was launched, bringing this tech straight into our daily lives. And now, as of 2023, we've entered a brand new era with the release of the Key 2 standard.
Section 2. Electromagnetic induction and resonance. The physics.
So how did we get from those giant electrical towers to the sleek little charging pads on our desks? Well, it all comes down to microscopic physics. The whole foundation of this technology rests on two absolutely crucial laws. First, Ampere's law tells us that when you run an electric current through a wire, specifically a coiled wire, it basically becomes an electromagnet, generating a magnetic field. That's exactly what's happening inside your charging pad. Then Faraday's law of electromagnetic induction kicks in. This law states that a changing magnetic field can actually induce an electromotive force, or a voltage, in a nearby conductor. So when you drop your phone's receiver coil into the charging pad's magnetic field, that field literally induces a fresh electrical current right inside your phone. And this brilliantly illustrates the two sides of the tech. If you look at the complex engineering schematic, the DC to AC inverter, the capacitors, the primary and pickup coils, it seems super daunting. But then you look at the beautiful simplicity of the magnetic flux lines transferring power across that physical gap. It's quite literally throwing energy across an invisible bridge. Now, there is one slight catch here. To create that changing magnetic field we just talked about, the charging pad has to use alternating current, or AC. That's where the electron flow is constantly reversing direction. But your smartphone's battery, it can only store direct current, or DC. To solve this, your phone is equipped with this tiny little device called a rectifier. It takes that chaotic alternating current and essentially forces the electrons to flow in a single steady direction so it can safely charge your battery. As this technology has evolved over the years, we've seen a real shift in how these energy fields interact. Basic inductive coupling requires your devices to be in very close proximity and perfectly aligned with each other. But with resonant coupling, the transmitting and receiving coils are actually tuned to share the exact same high resonance frequency, typically somewhere between 100 kilohertz and 10 megahertz. By doing this, the power can travel much further and far more efficiently. In fact, that's exactly how that MIT team managed to light a bulb from 2 whole meters away.
Section 3. The secret digital handshake. Device validation.
Okay, think about this for a second. If your charging pad is just sitting there, constantly ready to project a magnetic field, why doesn't it instantly heat up every stray paperclip or set of keys you accidentally drop on it? Well, it's all thanks to a highly exclusive club interaction. Right before a single drop of power is transferred, the pad and your phone have a very structured, secret conversation. Step 1. The pad detects a change in capacitance, which just means it senses something has been placed on top of it. Step 2. The base station sends out a highly specific 8-bit data string. Step 3. Your phone then has to validate itself by responding with its signal strength. And finally, Step 4. The base sends out multiple digital pings to figure out the optimum position.
So the crucial point here is that power will absolutely not flow until this precise 8-bit validation is totally complete. It's what keeps you and your random metallic objects perfectly safe. Section 4. The Qi2 Charging Revolution. Solving the pain points. Now, despite all this incredible science, early wireless charging definitely wasn't perfect. I'm sure many of you have woken up to a completely dead phone just because it was sitting slightly off-center on the pad, right? The sources outline a few really common frustrations. Because the power transfer is indirect, there's an inherent loss of energy, and that loss usually manifests as heat, which is why your device gets so hot to the touch. But the biggest culprit for severe inefficiency, by far, is coil misalignment, which is only made worse if you have a thick, bulky phone case. To finally fix these headaches, the Wireless Power Consortium introduced the brand new Qi2 standard, which splits devices into 2 distinct profiles. The Extended Power Profile, or EPP, uses standard existing technology without magnets. But the real game changer here is the Magnetic Power Profile, or MPP. This profile actually incorporates Apple's MagSafe technology into a universal, industry-wide standard. By using a ring of magnets, it physically forces perfect alignment between the transmitter and receiver coils every single time you put it down. And that brings us to the sleek new official Qi2 logo that was introduced in 2023. With over 351 different manufacturers collaborating on the standard, including all the major smartphone brands, spotting this little logo guarantees you're getting perfectly aligned, much faster, and noticeably cooler charging across a huge diversity of devices. It basically eliminates the guesswork and all that wasted energy. Section 5. Wireless Charging the Future. Smart Cities and EVs. All right, let's move out of the bedroom and see how this builds from our nightstands to the massive scale of a smart city. Just imagine pulling into your garage, or maybe even just waiting at a red light, and your electric vehicle instantly begins charging automatically. No massive, heavy cables to wrestle with in the rain or the snow. That is the ultimate promise of scaling up this exact same induction technology for electric vehicles. And hey, this isn't just science fiction anymore. Detroit has actually already built 400 meters of wireless charging road right into the asphalt for pilot testing. By installing these electromagnetic coils directly underground, a car's battery can be charged through inductive charging while it's actively driving down the street. It's an amazing concept called dynamic wireless power transfer, and honestly, it could completely eliminate range anxiety for EV drivers forever. Now, if you're worried about crazy energy loss at that massive scale, the data is actually incredibly promising. According to the SAEJ 2954 standard, which utilizes a specific 85 kHz resonant frequency permitted for EVs worldwide, researchers have demonstrated an efficiency of around 85%. As the source material points out, this makes it highly competitive and remarkably similar to traditional wired chargers, just without any of the physical hassle. Well, we've covered a lot of ground today in this explainer. We started all the way down with the microscopic dance of electrons, guided by Ampere's and Faraday's laws. We saw how the new Qi2 standard is using magnets and secret digital handshakes to make daily phone charging totally effortless. And we've even looked at how massive resonant coils are turning ordinary asphalt into electrified highways. It's just an incredible structural journey from basic magnetic physics to massive civic infrastructure. This invisible magic of wireless power is fundamentally changing how we interact with the world around us. So I want to leave you with this thought. As this technology continues to evolve, effortlessly bridging the gap between our power grids and our daily lives, what wire are we going to cut next?